Welcome back to another BGCSE past paper review. Today we are continuing with the 2021 Physics Paper 3, and now we're going to review Section B. What I'm going to do at the end of this review, I'm going to put the clickable link on top of this screen, somewhere to your right. You will see the review for Section A. So if you have missed the review for Section A, you can always go back and review that portion. Now, please remember that Paper 3 determine if you get A or a B. So please make sure you get maximum marks as best as possible from your Paper 3. Now, Section B contains 3 questions. You're going to choose 2 out of the 3. My suggestion to you is that you read through all the questions in full and make sure you answer the 2 questions that you can get maximum marks from. Some questions start easy and then you end up in problems as you go along. So read through them carefully. All right, so what we're going to do is to jump into our first question. And the first question is on question 5, and it's about heat capacity. So as the question states, is that question 5 is that this question is on heat capacity and specific latent heat. Now, what they ask us in the first part of this question is to distinguish between the terms specific heat capacity and 2 specific latent heat for 2 marks. Now, what I'm going to do first is to define both terms. And so, specific heat capacity is the amount of heat required to change 1 kg of a substance by 1 Kelvin, or you can also state this by 1 degree Celsius as well. Doesn't matter. Now, the specific latent heat now is the heat required to change the state of 1 kg of a substance without any change in temperature. So notice what is happening here. There's a change in state. This is not how you answer the question. I'm only defining both terms so we can actually able to distinguish between them. Yeah. So now for the answer. And once answering this, just to point it out, right? Again, you can actually define the terms and say, okay, specific heat capacity is this, while specific latent heat is this. Now, what actually make them different are 2 important factors. For specific capacity, as you notice right here, is that there is no change in state. However, for specific latent heat, there is a change in state. For specific heat capacity, there is no change in temperature. But for specific latent heat, there is a change in temperature. Okay? There is no change in temperature for specific latent heat. So specific heat capacity, the change in temperature. For specific latent heat, no change in temperature. So these 2 properties is actually what make them different. All right, that's what distinguish between both. All right, so let's jump into the next part of this question now. And this part B. So part B is a figure 5.1 shows the apparatus used by a student to determine the specific heat capacity of aluminum. Now, if you notice the apparatus here, you have a thermometer, awesome. You have an insulation that is encasing the block of aluminum. Now, aluminum that is in this, it will be transferred to it from the immersion heater. The immersion heater is connected to a circuit right here. Notice there's a voltmeter right here, there's a ammeter right here, and there's a variable resistor right here, and there's a low voltage DC supply that is right here. All right, so once this circuit is switched on, current will be supplied, the heater element will be getting hotter and supply heat to the aluminum block. Now, it said describe how the apparatus shown in figure 5.1 could be used to determine the specific heat capacity of aluminum. So how we're going to do this now, let's just outline this real quick. So I'll just get into another screen. And to do this, we're going to outline a number of steps. I'm going to do it by step-by-step process, right? So the first step is to determine the mass of aluminum block. Okay, that's the first thing you want to do, determine that mass. If you want to find that mass, you're good to go. The next thing you want to do is to determine the power and energy of the heater when used for a specified time. And I'm going to tell you why I use a specific time. And you're going to see it based on what I'm going to do with these formulas. Now, to find the power, you have to know the current, which is I. You have to also know the voltage, which is V. And so you have a voltmeter will tell you your voltage, your ammeter will tell you your current. And as noted right here, you'll read these from the meters. So you're going to explain that you'll read the meters, the voltmeter and the ammeter to get your value of voltage and current. And then based on that, you're going to calculate the power. And from your power, based on how long, that's why I put specified time here, based on how long you use the heater for, then you will know your time. And from your time, remember that power times time give you energy. And so if you multiply IV, which is power, times time, you get your energy used by the immersion heater. Now, the third thing you want to do is to measure the initial and final temperatures of the thermometer. That is before you turn on the circuit and after you turn off the circuit, just as you turn it off. So you're going to also mention that you check your temperature just before you turn on the circuit and just as you turn off the circuit. Okay, so you know exactly the amount of time, the amount of temperature involved in there. And of course, you're going to use that now to determine your difference in temperature. So what you're going to use now is use a formula that the formula going to be based upon the heat supplied by the heater equals the heat gained by the aluminum to find the specific capacity of aluminum. All right. And so let me just give a quick equation they're going to use again. Remember now, IVT is the energy supplied by the heater, as we mentioned up here. And it's going to equivalent to the heat gained by the aluminum as well. And so the aluminum right here is going to be the mass times the specific capacity times the change of temperature. And that's why the thermometer is very important to determine the difference in temperature. And so you're going to make the specific heat capacity the subject of the formula, which is going to equals to the energy, which is IVT, divided by the mass times the change of temperature. All right, and that's how you find the specific capacity. Of course, you're going to explain this in words as well to earn your 4 marks. But of course, you can simplify and actually outline formulas as well in your explanation. All right, so let's go to the next part of the question now. This is part 2. Is a calculate the specific capacity of 280 grams of aluminum block if temperature rises from 27 degrees Celsius to 53 degrees Celsius in 12 minutes when the potential difference across the heater is 4.5 volts and the current flowing in the heater coil is 2 amperes. That's a lot of information. But anyhow, let's break it down piece by piece. That's most important. 3 marks. Nice 3 marks. This is sweet. All right, so first, the formula. If we want to use the same formula we just mentioned earlier, that's IVT is equal to MC change of temperature. Again, IVT is energy supplied by the heater. MC change of temperature is the heat gained by the aluminum block. Again, we already worked this out, but we know what the specific capacity formula will be. So let's now substitute our values into this. So here now we have our 2, which is our current. We have our 4.5, which is our voltage. And then we have times 720. There's no 720 in this question, but guess what? We have 12 minutes. So we need to convert the 12 minutes into seconds by multiplying by 60. And so therefore we have 720 seconds. Divided by the mass of the aluminum block, which is 280 grams, multiplied by 26, which is, 26 is a change in temperature. So remember, we moved from 27 to 53, and so there's a difference in 26 degrees Celsius. That's a difference in the temperature right there. And so from all of that, what we're going to get here now is 6,480 divided by 7,280. And so as a result of that, our specific capacity of the aluminum block is 0.89 joules per gram per degree Celsius. So the unit is also important, all right? All right, so next part of the question now is a state an assumption that must be made when using the results obtained to calculate the specific capacity of the metal. And this is a 1 mark question. So the assumption that must be made, even though the apparatus you have an insulated case and all of that, but what must be made is that no heat was lost to the environment, right? That means all the heat that is supplied by the heater actually go into the aluminum block. So you can state it as this as well, that the total heat lost by the heater is the heat gained by the aluminum block, all right? And that is the assumption that they must make. No heat was lost. Because if heat was lost, then definitely if you use the power and the energy by the heater, all of that will not go into the aluminum block. So that will be half a little bit, right? All right. So part C now, It's an electron immersion heater of power rating 50 watt is placed in some ice as shown in figure 5.2. And notice figure 5.2 is on the right here. All right, so we have two things. If you notice here is a 12-volt power supply that is here. Here now we have the same power supply, but guess what? No power is on here. All right, and of course you notice the difference in water melted. One is higher than the next. All right, so let's look at what they're actually asking us here. Now for part one, it says calculate the specific latent heat of fusion of ice after 150 seconds. 24.7 grams of ice found to have melted due to the immersion heater, and it's for 2 marks. Now, when you hear that latent heat of fusion, please know what you're talking about from solid to liquid or liquid to solid, right? If we talk about heat of vaporization, you're talking about liquid to gas or gas to liquid. Okay, just to mention that. All right, so next thing here, all right, as we're going to quickly just point this out and just to make sure we have space to calculate right here, quickly. The first thing I want to outline again is a useful formula. And so the useful formula is that power is equal to the change of energy over time. So energy is going to equal the power times time. You can ignore this division slash, right? It's not supposed to be there. Just power times time, all right? So let's ignore that. It means nothing. That's a typo. All right. So what we're going to do here next now is to find our power or energy. And so the energy now, as we know, our power already, which is, look, we'll go back in the question right here, is 50 watt on top. You can see it in the statement on above that is minimized. And then you're going to multiply that by time, and time in the question here is 150 seconds. That is our energy supplied by the immersion heater, 7,500 joules of energy. All right, now, again, remember this is another useful formula here that you need to remember, is that the energy supplied by the immersion heater must be equal to the energy that is gained by the ice or needed to melt the ice. And so since there's no change of temperature, because when you change of state, when you just change state, there's no change of temperature. So when you just change from solid to liquid or liquid to solid, there's no change of temperature. And so all we need here is the mass of the ice multiplied by the latent heat of fusion of ice. But good thing they asked us to find the latent heat of fusion because we don't have that. So the latent heat of fusion of ice now will equal to the energy divided by the mass of ice itself. And so therefore the latent heat of fusion is going to be 7,500, the joules of the energy that we calculated earlier, divided by the mass of ice that's given in the question. And that will equal to 303.64 joules per gram. Okay? All right, so notice there's no degrees Celsius because there's no change in temperature. All right. Now going to the next part of the question, you say why is there a need for a control? All right. So the first thing, if you notice in the diagram before, we have a control there beside the actual experiment. And really and truly, a control is just used to compare results. All right. So I'm going to say it like this: is to compare the process of melting by the heater, which is the experimental results, to the process of melting under normal conditions, which will be our standard. So you want to compare your result to a standard. So just in case you get some abnormal results, you can refer back to your standard melting process and know, okay, that something is wrong. It's melting too slow, melting too fast. Because just in case the heater melts less water than what was melted in the standard or the one with no power or the control, they know that the heater itself is not working properly, right? Because if you apply more heat, then you should get more water that or more ice being melted. If that is not happening, you can go back to this and say, okay, something is wrong, and make an adjustment and do the experiment more than once to make sure you get average and all those type of stuff. All right, so let's jump on before we run out of time. Let's quickly move on. So part D now is a container holds a liquid. As the liquid evaporates, the temperature of the liquid decreases. Use the kinetic theory to explain why this happens. So when I use the kinetic theory now to explain why the temperature decrease in a container as liquid evaporates. So the first point to note is that the temperature is proportion to the kinetic energy. Okay, so higher temperature means higher kinetic energy. Kinetic energy means the particles move faster. So higher kinetic energy means particles are moving faster. All right. So as temperature increases, particles will gain kinetic energy and move much faster. So the next point to note right here now is that particles with high kinetic energy, again due to higher temperature, will move to the top of the liquid, And as the one with higher energy move to the top, the one with lower energy will fall to the bottom. And that continuous up and down movement, rising and falling of particles, is what we call boiling. All right? So boiling will take place there. However, now, as particles with higher energy escape the liquid or the surface of the liquid by what we call evaporation, it will leave behind particles with lower kinetic energy. And since the particles that leave with lower kinetic energy now, again, because of the equivalence or the proportionality to temperature, then particles with lower kinetic energy in the container is equivalent to lower what? Temperature. Because remember the first statement, temperature is proportional actually to kinetic energy. Okay, it says proportional to kinetic energy. All right. Now, what is a thermocouple? That's the next part of the question right here. For 1 mark, a thermocouple is simply a device made up of 2 wires of different metals forming a junction that is being used to detect or measure temperature or radiation. Okay, so there are different metals that make up the 2 different wires. Okay, so just again, S supposed to be at metals right there. All right. Now I'm gonna give you a diagram of the thermocouple, a simple diagram of the thermocouple. So a thermocouple will look something like this. You have the junction. Notice you have a blue and a red wire, so which indicating 2 different types of wires of different metals, and they will connect to a connector, and the connector will be pretty much the same. That goes to a voltmeter, and then it will record the readings according to the amount of radiation or temperature change that you will see it indicate on the voltmeter. All right, so that's what a thermocouple is. Now, the next part of the question here now is said, which is E2, it said give 2 benefits and 1 drawback of using a thermocouple for 1 mark. No, I don't think this is actually 1 mark. I think I made a mistake there. I think I made a mistake, but this should be a 3 marks, I think. All right. Yeah, I think it's 3 marks. I think so. I really, really think so. But anyway, it doesn't matter. The fact that there's actually 3 marks in it. That's supposed to be 3 marks, but ignore it. It don't matter. Once we answer this question, and understand information, we find. All right. So here I'm going to give you some benefits and some drawbacks. Again, it's a 3 mark question based on the examination, but I just want to outline more than what the marks actually give or the amount that's actually there. And so some of the basic benefits, I mean, you may have more, but some of the basic benefits here is what is a fast response type of instrument. Is that it can read wide range of temperatures compared to a regular thermometer or a mercury thermometer. Most mercury thermometer, like the simple laboratory ones, they will just stop at 100 degrees Celsius or 110 the most. And so it can read way above that and also below that as well. And also, in terms of fast response, it's quick because it's immediate instead of expansion, because the mercury will have to expand over a period of a couple seconds, I will say, but this one is actually fast. It's kind of long lasting again because the type of material is made up of. However, now some drawbacks is that 1, it could be less accurate, definitely, because a number of reasons. Because again, you're using wires. Wires could have different resistance. Not only that, again, the equipment, and if the wire is also oxidized, then that can also cause slower readings as well, or if they're coated with some form of chemicals. All right. Again, there's a possibility of rusting may take place and corrosion may take place in the wires as well, so that's a possible drawback again. Again, based on the type of thermocouple that you're using, some of them may need installation before you use them, or some of them may also need to change the batteries or to install batteries. So, for example, let's say you're going from one location to another location to do some testing of temperatures, and you have a thermocouple. The batteries may be working now, but on the journey, the battery may die without you even knowing, and then you have to change those batteries. You reach a station 2, you realize that no batteries, or you have dead batteries. So that could be a next drawback right there. A mercury thermometer, you just stick it in, get the temperatures, you move on, and that's it. There's no need to think about electrical components, not batteries. All right. Now, question number 6. And we're kind of riding the waves a little bit faster now. All right. So this is properties of waves. All right. So now question 6. Now let's go to the first part of this question. It's a question 6 about waves and their properties. And so the first part is part A. So waves can be longitudinal or transverse. is to give one difference between longitudinal and transverse waves for 2 marks. One difference for 2 marks. You're pretty lucky to get that. That's a big deal. One difference, 2 marks. All right. I don't know why they have done that. I guess it's to make sure the marks are distributed equally, or maybe the technicality of the question. But these differences are pretty much how these two waves are different. So longitudinal waves, again, the wave particles, they are parallel to the direction of the wave, right? So they run along the direction of the wave direction itself. Those are where the particles are actually moving, or the vibration. In transverse wave now, the particles are perpendicular, which means right angle to the direction of the wave. For longitudinal waves, they produce rarefactions and compressions, while transverse wave, now they produce crests and troughs. All right. The next part of the question now is said draw a fully labeled diagram to illustrate a longitudinal wave for 3 marks. And don't worry, I'm not going to take up a lot of time to draw this, so I'll pre-prepare this for you nicely. So let's just shoot it on. And so notice there, what you need to outline though with longitudinal waves, you have some portions that you have the lines are close together and some that the lines are further apart. All right. And they pretty much will kind of create a nice equal pattern throughout the entire motion. So along this pathway, that's where the direction of a wave will be. So the wave will go in that direction. Well, it can go in the opposite direction, but it must indicate where the wave is going. That's also important. Where the lines are closer together, we call those areas compressions. All right. So those closer lines, they are compression. And the lines that are further apart, we call a rarefaction. Okay. And the distance between two compressions, equal points between two compressions, we call those the wavelength. So the central, I'm going to put it this way. The points between two central parts of compressions is pretty much the wavelength. All right. And so that will be a simple diagram of a longitudinal wave. All right. So now part 3 now is to give one example of a longitudinal wave and an example of a transverse wave. And for this longitudinal wave is like sound wave. Transverse wave, pretty much light wave, and any other member of the electromagnetic waves. All right. Now for part B, now we say a tsunami is a giant water wave. All right. It may be caused by an earthquake below the ocean. Waves from a tsunami have a wavelength of 1.9 times 10 to the 5 meters and a speed of 240 meters per second. Here's actually calculate the frequency of the tsunami, but let's outline some things that we need to know. We have our wavelength, we have our speed, and they actually calculate the frequency. But what you need to remember is that speed is equal to frequency times wavelength, so therefore frequency is equal to speed over wavelength. And so here now our frequency is going to be 240, which is our speed divided by our wavelength, which is 1.9 times 10 to the 5, which is the same thing as 190,000. And so as a result here, our frequency will be 0.0013 hertz. And hertz is the same thing as per second. So you can have 0.013 per second, okay, which is the same thing as an hertz, because frequency is 1 over t, and t is 1 over frequency. All right. So they are the inverse of each other. All right. So part C now is that the shock wave from the earthquake travels at 2.5 times 10 to the 3 meters per second. So that's the speed that the shock wave is traveling at. The center of the earthquake is 6.0 times 10 to the 5 meters from the coast. It's a calculate how much warning is given of the arrival of the tsunami at the coast after the tremors are felt at the coast. So here we have the distance and we have the speed. That's an awesome thing. And then we can use that to find time. All right, so we know that speed is equal to distance over time, so therefore time is equal to distance over divided by speed. So therefore our time going to be our 600,000 is based on our 6 times 10 to the 5. 600,000 divided by 2,500, which is our speed. 2.5 times 10 to the 3 is 2,500. And so therefore, as a result, our time going to be 240 seconds, or in minutes, going to be 4 minutes. So divide this by 60, you get 4 minutes. All right. So you have a 4 minutes warning or a 240 seconds warning. All right. Next part of the question now, part D. It said a water wave travels from deep water where its speed is 25 meters per second to shallow water where its speed is 15 meters per second. The angle of incidence is 30 degrees. Is a calculate the refractive index of this at this boundary, and this for 2 marks. So to find refractive index, only thing you have here is speed and you have an angle. So the only thing you can use to find refractive index, because based on the formula for refractive index is equal to sine angle of incidence over the sine the angle of refraction, or you can use it based on what we have here is the speed in the deeper water divided by the speed in the shallow water. Okay, and so as a result here we have a refractive index being 25 divided by 15, which equals to 1.6. There's no unit for refractive index because it's just a ratio of how fast the wave will be traveling in deeper water compared to the shallow water. And it travels 1.6 times faster in the deeper water. Okay, that's what it is. All right. Now for part D, or I think this is E, actually E. All right, it said, here it said that a water wave travels from deeper water where its speed is 25 meters per second to shallow water. All right, where its speed is 15 meters per second. The angle of incidence is 30 degrees Celsius. Remember that N was 1.6, and it's a calculate the angle of refraction here. So we have our refractive index already, which is good. All right, and so for part 2 now, because D part 1 we finished D part 1, so this is D part 2. All right, so now we'll calculate the angle of refraction, and so based on this formula, the refractive index equal to sine theta 1 over sine theta 2, or the sine of incidence over the sine of the angle of refraction. Now, 1.6 as we calculated earlier, so equal to sine angle 30 degrees Celsius, which is the angle of incidence, and over sine the angle of refraction, and that's what we want to find. So let's make that be the subject of the formula now. So therefore, we're going to have here now 1.6 equals to 0.5, which is sine 30. And so sine R will equal to 0.5 divided by 1.6. And so therefore, we get our sine R being 0.5 over 1.6. That equals to 0.3125. And so we're going to find the inverse of this. All right, so we're going to find the inverse of that. So the inverse of that would be R equal to the inverse of that, which equivalent to about 18 degrees. 18 degrees. It's actually 18.2 something. Okay, but round off to be 18 degrees. All right, so that's 18 degrees is our angle of refraction. All right, so part E of this question now, we said that the principal axis of a convex lens, so there's a convex lens, very important, is PQ. So PQ, that long line there, that's the principal axis. It said the center line is XY. So the center line is the center of the lens actually, right? It's an object 2 centimeters high is placed 2 centimeters to the left of the lens. The focal length of the lens is 3 centimeters. Now, on the axis provided, draw a full-scale ray diagram showing the formation of an image as for part 1. That's a 3 marks, yeah? So I'm not going to do all of this together. And then part 2 now is a measure the distance of the image from the lens. And it's a measure the height, which is part 3, measure the height of the image. So I'm going to use this opportunity to kind of run through some basic things that you need to know when it comes on to lens, especially convex lens in drawing objects and image and all that stuff, right? So watch this now carefully. All right, so based on the question there is minimize, yeah? So what I'm going to do now is to pull this out and use that now as our base. And what I'm going to do here now, I'm going to use some pointers, some rulers. All right, a very important thing. Let's go back to the question, yes? And so we state that the object was placed 2 centimeters high. That means the height of it is 2 centimeters and it's placed 2 centimeters to the left of the lens. So on this side now, let's put our ruler there. And we're going to measure 2 centimeters there. Actually, 3 centimeters. The focal, let's do the focal length first. And before we put on the object. So the 3 centimeters here is our focal length. And so let's call that F, focal length. And if we double that line here, we're going to have, again, another 3 centimeter there, which is a 2Fs. So I put my ruler a certain way, so the 6 to 3, that's still 3. And from 3 to 0, it is still 3. So that's just turn the ruler backwards. That's easy way to do it. Doesn't matter how you do it, though. Don't really matter. You can turn the opposite way and start from 0 from the XY line. Really don't matter. It's just how I manipulate it. All right. Once I get my 3 there, let's go to the opposite side because F must be the same on this side. So let's put it on this side as well. So from the 6 here to 9, there's another 3. So let's call that F as well, right? Just because we're going to need those points. So once I get a convex lens, the 3 points that you must establish first is a focal length. On either side, they're the same, and then they can also indicate your 2 Fs as well, right? That's the first thing you want to do. Do that first. Now, next thing you want to do here now is to put your object at a specified distance, and the object is placed 2 centimeters from this line. So 2 centimeters be at the 4 point right here, right? So this is 1, 2. From this line here, come over is 2. Right? Mine is slightly off. You're going to see the 6 line is slightly off, but don't worry. I can have a way to adjust that. Don't worry. All right, so I'm going to slightly put that there. That's my object. That's my object right there, 2 centimeters away from the lens on the left. All right, let me just take off these rulers. And the next thing I'm going to do here now is to draw important line. Some important lines, as a matter of fact. The most important line. No, let me not say most because none of it is more important than the other. But the first important line, what I believe is this one. From the top of the object, where the principal axis and the center of the lens intersect, a line must be drawn straight through. That's the first line. Don't worry about nothing else. Draw that first line. So let's put that first line there. The next thing you want to do is to do this. Another important line is to draw one on top of the object all the way over to the center of the lens. But make sure that the ruler is straight. Make sure that the 90 degrees angle is all about, because if you have the ruler slanted a little bit, your lines will be a little bit off. I'm going to tell you that, so be careful with that as well. So what you could measure is, since the object is 2 centimeters high, you can measure 2 centimeters here, and you can also measure 2 centimeters here as well, and know exactly where the 2 lines will meet, and then you strike your line across like that. All right, so once you make that line, so those are 2 lines now. So notice the first line, the second line. Now let's go to the third line, which is going to be very, very important. This third line now will strike the 3 points, which will F on the opposite side of the lens, go through with the top of the object, will actually line up to the center of the lens, and it should intersect on that line that you drew, the first line that you drew. And so here we have that line. All right, so let's move the ruler there. So now you complete that line. So wherever the line intersect right here to the principal axis, that's where the image will be. So that's the image right there. Okay. So notice the image can't be formed right here because these lines are actually diverging or separating on this side. They converge right here. So that's where the image will form. Just to kind of make you understand. This is an easy way to go through lens drawing these lines, right? All right. So once you have established now, the next part is said that that's your 3 marks right there now. We actually could label the distances and all that. You could do that. Measure the distance, mark the distance on the line. You could also do that. That's fine. Up to you if you want to do that. It's to measure the distance of the object from the lens. You're going to take your ruler and measure the object distance here. For me, it is going to be 6 centimeters based on measurement. And then the image will also be 6 centimeters high as well. All right, those are 1 mark questions. All right, so that's an easy way to do lens question or to draw image object relationship based on how they are formed, either in front or behind. And just a point to note, let me give you extra information as well. A point to note here that as extra information here, that image is upright, it is virtual, and is also magnified. Okay? And a matter of fact, the magnification is actually 6, which is the height of the image divided by the height of the object, which is 6 divided by 2 says 3. So the magnification is 3. That means the image is 3 times as large as the object. All right, so that's finished with that part of the question. So now we're on the last question, and this is question number 7, and it's about radioactivity. All right, so let's jump into the radioactivity question now. All right, and so this question is about radioactivity. So gold has one stable isotope and 36 radio isotopes. Wow. All right, now the first part of the question is one of the isotopes, which is gold 198, decays by emitting a beta particle. Define the term isotope. And it's for 2 marks. Now, an isotope is a different form. Notice I'm saying now it's a different form of the same atom. Same exact atom, but it's a different form, which means if it is the same atom, it must have the same number of protons. Once this number of protons are the same, the atom is the same. No matter what else is different. The number of proton is what defines the atom. So no two different atoms will have the same proton number. Cannot. In other words, they can't have the same atomic number. Right? That's why the proton number is called atomic number, because that is what defined what the atom is. Okay? However, now, since I said that there are different forms of the same atom with a different mass, and a different mass is due to a difference in the number of neutrons. All right? So that's what an isotope is. Now, it's to explain how a beta decay occurs for 2 marks, right? Beta. So the beta decay is 1. The first thing I want to notice right here, now the first thing that takes place is that a neutron is converted to a proton. All right, careful and listen this well. A neutron is converted to a proton. What I want to point out is that proton and neutrons are found in the center of the atom. In other words, they are found in the nucleus of the atom. Proton and neutrons, the number of protons and number of neutrons together, the sum of them make up the mass number, okay? So if the neutron converts to a proton, what happens there, the proton number changes, which means the atomic number increases. Or I can say there's an increased number of proton. But you know what happened here? The mass doesn't change. You know why? I'm going to talk about that in the third point. The higher the higher the particle, the high energy particle, which is the beta particle, will be emitted. So once that is converted, the particle that actually causes it will actually what? Be emitted, which will be given off. All right? And now what I want to talk about right here now, the remaining part of the atom, or the remaining portion of the atom, experience an increased atomic number. So the atomic number increases because you have more proton, and proton is the same as atomic number, but there's no change in mass. Why there's no change in mass? Because neutron convert to proton, and since they're just interchanging, the mass number is the sum of both. So it's like you have let's say you have 2 plus 1 instead of 2 instead of 1 plus 2. The same thing. 2 plus 1 is 3. 1 plus 2 is still 3. So interchanging between neutron and protons. That's all they're doing. So the mass number must be the same. Okay? And that's how beta actually works. All right. So let's go to the next part of the question here now. Say, this is part B. It's a figure 1 shows a sketch map of a research station not drawn to scale, where environmental scientists have found that water flowing into one part of a lake is polluted. And notice this diagram here. You have a generating power plant, you have a sewage treatment plant, and here you have the area of polluted water. So what is polluted on this side? This is a research farm, right? So this part of the question now, we said, explain how the radioactive isotope gold 198 may be used by the environmental scientists to detect where the pollution is coming from, for 2 marks. I think that's kind of easy, 2 marks, to be honest. But anyway, let's talk about how we're going to get this, yeah? All right. Now, let's move to answering this. So let's kind of just minimize the screen a little bit, get those out of the way. All right, so the first thing I want to mention here now, right? Or the first thing I would do is this, is to place samples of gold 198 in the water or at the bank at GPP. Please don't write GPP on the exam. I'm just representing generating power plant right here. And STP, it is sewage treatment plant, not standard temperature and pressure, but the sewage treatment plant. All right, just a short. And please, you write out the words. Don't do what I'm doing right here. All right, write out the words, or let's put it in bracket then. Okay, and you want to do this at different times, and make sure I highlight in different times, because if you put the gold at the same time, you're not going to know which one is causing the pollution. So let's say you start with the generating power plant first, and you do your experiment, and then after finish that experiment, then you go to the sewage treatment plant and do the same thing. And you can do it, when I say different times, you don't have to be in the same day. It could be like weeks or a couple of days, and observe over a couple days or a few days. Okay, because sometimes it will take a little while to reach to that point, right? You're not going to be immediate all the time. So it depends on the flow of water and all of those stuff. The effect is not always immediate. So they must do it at different times, however. All right, the next thing now, we're going to test the polluted area to detect gold 198. I'm going to repeat, and again, you're going to repeat the steps for accuracy. Again, I like to do that because I like to make sure that, hey, my first result is the same every time, or similar almost every time. Now, we're going to test the polluted area for the detected gold. Let's say you put the gold at the generating power plant. It will travel all the way to the polluted area. But let's say when you put it at this is not showing up here, that means it's not reaching that point. That means this generating power plant is not what is causing the pollution. All right? And of course, if you put it at the sewage treatment plant and you see it there, then you know that the sewage treatment plant is causing the pollution. Because you can actually test or detect the gold 198 because they're radioactive, right? So you can do a radioactive test. Now, the detection will indicate the source of the pollution. So again, if you put it at the GPP and then you realize that it is showing up at the polluted area, that means it travels from the generating power plant all the way to the polluted area. If not seen it, that means this is causing it. If you put it at a sewage treatment plant and it show up at the polluted area, yes, the treatment sewage plant is causing pollution. If it's not showing up, then it's not what is causing the pollution. Again, you do it more than once for accuracy. All right. Let's jump to the next part of our question here now. And part C is an environmental scientist records how the count rate of a sample of gold 198 changes over a 5-day period. The data below shows the result. And so you have time, you have count rate right here, which is times 10 per second. And so the results are there. And then the first part of the question is to plot a graph of count rate of gold 198 and the y-axis. They're being kind of nice still to tell you which axis you're going to place this on, against time on the x-axis. So they really, really kind of tell you which axis you're going to use. But time is always on x-axis because time is the dependent variable, okay? So you can also use that as an indication where you place time. So time is generally on the x-axis because it is a independent variable. The count rate will be dependent, so you go on the y-axis, all right? But they've been nice and kind. All right, so by plotting the graph, you get something similar to this graph. All right, the lines that are there, but you may not see them properly on your screen. But some small fine lines are there. So this is a 0 line here, indentation of labeling. So we label our y-axis. You need to label axis very importantly, and put your proper units as well. You need to give a title. Also, you need to make your points be very fine as possible. Well, actually, they need to be obvious, but not big and bold and odious, but obvious, not odious. All right, and also you're supposed to have a line, smooth, nice line connecting the points. All right, not no zigzag line, because zigzag line, that is really not showing us anything. There's going to be plenty errors in that. All right, so the line's supposed to be as smooth as possible. That's very important. That's also all you're in your marks. All right, so let's jump to the next. What they're asking us here is from the graph plotted, determining. So we're determining a number of things here. I suspect, and so one we're going to determine here the half-life of gold 198, and so what you need to do is to put your ruler where half-life is, and since it started a count rate of 6 when it was 0 time, the count rate was 6. So therefore, half of 6 will be 3. So go straight across to 3. And this will be approximately there 2.65 days. So again, on the x-axis is in days. So it'll be 2.56 days. All right. So 2.75 will be a little bit off of the ruler itself. I mean, the lines are there. They're very fine. They're kind of dull in the background, but that's the best I could do. And so it's about 2.65 days. If you do it, then you get a little bit, probably 2.6 flat. Yeah, you still safe because they want to give allowances or for plus or minus values, right? But it cannot be 2 way off. It cannot be 3. It cannot be 2.5. Right. So those things are so have to be really close to 2.6. All right. All right. So let's move that off. Now we'll go to the next part. Now, so the time when the count rate is 4.57 times 10 to the 10. And again, on the x-axis, on the y-axis, these are actually by times 10 to the 5. Okay, that's a mistake, right? It's be not 150, but 10 to the 5. All right. So what we're going to do here now is with the ruler where this is at. All right. So the 7.5 line is 3/4 way up, and you're going to match up where it falls on the x-axis. And so this falls at 0.8 days. So less than a day, you get that. So it's less than a day actually. All right. So anywhere here, less than a day. All right. So the next part of the question here now is said that the count rate at 3.8 days. So look for 3.8 days for the ruler at 3.8 days. So here is 3.75. And so 3.8 is pretty much right there. And so you're going to look at where the line go all the way over to the y-axis, and that's going to be about 2.2 times 10 counts per second. All right, and so that now answered that part of the question. So let's go to the next part of the question here. And this is part 5. It's a gold 198 is used in the treatment of some cancer and other diseases. Give 2 reasons for the use of gold 198 in nuclear medicines. And it's for 2 marks. And so one, it has a short penetrating range. That means it don't penetrate through the body too much. All right, so it pretty much stays in the cells because the range is really, 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 really short. And so because the penetrating range is so short, then it will affect the target cells. So it can damage it. So let's say it's cancer, for example. It could kill the cancer cells, all right, without causing any damage to the surrounding cells. So here it said, while affecting the target cells, it caused little to no damage to the surrounding cells. All right. And again, because of its short penetrating power. It is relatively short. You have a relatively short life. So the short life is really, really short as well. It will not stay too long or forever in your body causing effects. So you're going to break down really fast over a period of time. And so generally, it is relatively safe. All right. So next part of the question here, it's a gold 195. I think this is the last part of the question. It's a gold 195, which is a different type of isotope now. Has a half-life of 186 days. A sample of gold 195 has a count rate of 1,000 counts per minute. How long will it take the sample to fall to 125 counts per minute? Now, there's an easy way out of this, and there's a little more technical way out of this, depending on how you like your mathematics. So, let's do the easy way out first, right? I know we prefer that. So the easy way out is this. You want to reach down, you want to move from your count rate 8,000 to 125. So what you're going to do, you have 8,000, half of that. So in half time, you're going to break down into half. So you get 4,000. Then you go half of that again, which is 2,000. Half of that is 1,000. And half of that is 500. And half of that is 250. Then half of that is 125. So you reach 125 now. How long it takes to reach there. And what you need to know that the half-life here is 186 days, right? So how many half-lives? The number of arrows that I drew right here actually represent the number of half-lives. The number of arrows there is 6 arrows. That means it takes 6 half-lives to reach to 125, right? So what you're going to do is multiply that now by number of days. So 6 half-lives multiplied by 186 days give us 1,116 days. All right? So that's how long it will break down. And if you have time to spare and want to just go ahead and write the number of weeks, the number of months, the number of years, don't matter. Because 159.43 weeks, it will be 37.07 months or 3.09 years. All right? So that's the short, easy method. All right, let me just finish up with the longer method here, because this is the last question, by the way. So let's go to the longer method, just in case you may need it. Or when you move on to your AP or your SATs, you can know to use it. But of course, you can use it in your basic national exams as well. All right, so for the same procedure, right, is that we're now using the algebra way or the algebra method, is knowing this formula, C equal to CO times half to the power of T over H. All right, let's break down that to what all of those mean. So C is the final count, all right? CO is the initial count, and T is the time taken, and then H is the half-life. All right? So what we want to find now, based on this question, we want to find the time, how long, we want to find T. Okay? So now that's what the problem is, to find T. If you ask us to find this, then it'll be sweet and easy. If I ask to find the final count, then it'll be nice. But unfortunately, I ask to find T, so that's what the problem is. So let's break this down using algebraical function. So based on the algebraical function, right here now, T equals to H, all right, times normal log. So ln is normal log. So you can look at the calculator, you see ln, which means normal log. You have a log button, which is different than ln. ln is normal log. Okay? And so it is H multiplied by the normal log multiplied by the final count over the initial count, all divided by minus normal log multiplied by 2. All right, I'm going to point out something here as well, because I know if you plug this in the calculator, try to do it, you're going to end up with some errors. So I'm going to show you what to do. So what you'll do, let's substitute first. So here we have our 186, which is our half-life. So 186 is our half-life. Our log is there. The final count was 125 counts, and our initial count was 8,000. So it's going to be 125 over 8,000 divided by 0.693. To work out the numerator, what you're going to do is press in the calculator the 186, then you press the ln, then you press 125 divided by 800. Sorry, this is supposed to be 8,000. This is supposed to be 8,000, not 800, 8,000. My mistake. I'm plugging in my calculator 8,000. So this is 8,000, not 800. Okay? So once you have done that, what you'll realize, you'll get a negative 773.552. Again, I'm pointing this out. This is not 800. This is 8,000 based on the question. So plug that all in the calculator. What you're going to get is that divided by, and if you plug minus log minus the normal log, 2 multiplied by 2, or just put 2, press 2, you'll get the negative 0.693. That's where this 0.693 came from. And so divide these two numbers now. What you realize you get here now is the same value that we get earlier. We got this value earlier, which is 11,116, which is 1,116. But this now gives us a decimal because of calculations, of course. Based on this type of calculation here, it is 2.237 days, right? So it's the same thing, run off to 1,116 days, pretty much the same answer. All right, so this is the end of it. And I want to say thank you for being here. Thank you for dedicating yourself to this very end. And I want to wish you good luck on the exams. Do well, and I will see you soon. Take care.